Morning, my dear students. How are you doing today? Cool. So today we're doing chapter 3.2 on linear functions. Honestly, this section is very easy. And I would recommend that with this video, you pretty much just need to watch it. You really don't need to take very many notes other than perhaps write down a few definitions. But really, I wouldn't bother writing down the notes, but I would watch the video and listen. I think that if you listen, you will learn it. You can write down a few things if you want, but mostly just listening will do. So the question in this section is basically this. Is a function linear? So last chapter we learned what a function was. It's simply a relationship between some input and output values. And if every input value, like 0, has one output value, like 158, that's called a function. So today we're going to determine if a function is linear. In the next few chapters, chapter 3 and chapter 4, we'll be working with what are known as linear functions. So the question is, can you recognize a linear function when you see one? So I'm going to give you an example first because it's really, really simple. A linear function is, for example, this one right here. When I was in college, I had a bet with my roommate that I could gain all the way up to 170 pounds by the end of the semester. We were working out and lifting weights, and our goal was to bulk up. And so I said, I bet I can get up to 170 pounds. And I did. And basically, I tended to gain about 2 pounds a month. So it looked like this. At month 0, when I started, I was 158 pounds. And after a month, I was 160. And after 2 months, I was 162. And after 3 months, I was 164, and so on. I was gaining 2 pounds per month. Now, if you were to make a graph, that graph would look like this. It would make a perfectly straight line because you're going up 2 pounds for every 1 month, 2 pounds every 1 month, 2 pounds every 1 month, 2 pounds every 1 month. And because it has a regular rate of change, it's going to be a straight line. That is a linear function. It's a function where when you graph it, you get a straight line. So today you need to be able to recognize if a function is linear by looking at 3 things: a table, a graph, and an equation. It's very easy to do. You can tell a function is linear from a table if it has a constant rate of change. And here's what I mean. Check this out. The months, are they going up by 1 every time? Plus 1, plus 1, plus 1, plus 1. So every month, it's just going up at a constant rate here. And here is my weight also going up by a constant amount. Yeah, plus 2, plus 2, plus 2, plus 2, plus 2. So what I can say is that for every month, I go up 2 pounds. The next month, 2 pounds. The next month, 2 pounds. The next month, 2 pounds. That's called a constant rate of change. I'm not gaining 3 pounds 1 month or losing a pound in the other month. It's constantly plus 2. And that is how you can recognize from a table that it is linear. How can you recognize from a graph if it's linear? It's even easier. Is it a straight line? Notice this blue line is straight, and because this blue line is straight, it's a linear graph. And this is a linear function. And you can tell from an equation if it's linear, if the equation looks like y equals mx plus b, or it can be rewritten as y equals mx plus b. For those of you who remember from last year, perhaps you might recall that this equation is y equals 2x plus 158. So my weight is 2 pounds per month plus the original 158. Y equals mx plus b. A linear equation is never going to have exponents, like it won't be x squared or square root, or it's never going to be like, 3 divided by x. It's always going to be something that looks like y equals mx plus b. That's how you can tell if it's going to be linear. Now, I don't expect you today to know how to come up with that equation yet, although some of you probably know it, but that's a section, the next few sections. All right, so let's do some brief exercises. Again, you don't need to write this down, but just do this kind of, watch the video and do it in your head with me. So here's a question. I'm going to give you 3 tables, and my question for you is, which of these 3 tables are linear and which ones are not linear? Take a moment, look at the tables, answer that question. All right, so let's check it out. So plus 2, plus 4, plus 2, plus 4, plus 2, plus 4. Does this seem to have a regular rate of change in the table? Yes, it does, and therefore this is linear. If you graph these points, you'd get a straight line. Now, sometimes your table is horizontal, so let's try this one. So plus 2, plus 2, plus 2, plus 2, plus 2, plus 2. It's all plus 2s. And here, plus 5, plus 5, plus 5, plus 5, plus 5, plus 5. It's all plus 5s. So is that a linear table? Yes. And if you were to graph it, it would be linear. Now, I took the chart from the first slide and I made a few modifications. So I said this, the first month I gained 3, and then I gained 1, and then I gained 1 again, and then I gained 3, and then I gained 2. Now, is that a linear table? No, because it's not going up at a constant rate. And when I graph it, look what happens. It's no longer a straight line, because some months I'm going up 3, and then I'm kind of flattening out and only going up 1, then I'm going up 3, so it's steep again, then I'm going up 2. So if it's not a constant table, you're not going to get a straight line. So it's not going to be linear. Easy, isn't it? Let's take a look at some graphs. Oh, wait, not that slide, this slide. Take a look at some graphs. The question is, which ones of these graphs are linear? Easiest thing in the world. This was a straight line? Yes. This was not a straight line, so no. This red one is a straight line, so yes. This blue one is not a straight line, so no. 10,000 points if you can name the shape of this blue one. Parabola. That comes up in chapter 7. This guy, no, that's not a linear function. It's not straight. And this one, it's a straight line that's flat. It has a slope of 0, but because it's straight, it is linear. So the linear ones are this one, and the red guy here. And the nonlinear ones are the blue one here, this blue one here, and this guy right there. Very easy. Is it a straight line? So it's linear. Is it not a straight line? It's not. See, I told you, you don't have to write that down. All right. This is a little bit harder to do, but can you tell from an equation if it's linear? It's linear if you can write it as y equals mx plus b. There are no square roots. There are no exponents. So let's take a look at it. Number 1, you think that's going to be linear? Yeah. Number 2, is this linear? Nope, because there's a squared. In fact, if you were to graph something with a squared, it would make a parabola. It's going to look like that. What about this guy? Has a square root. Is it linear? Nah. In fact, if you were to graph it, that one would look like, oops, I slightly did that wrong. That would look like this. It would go like that, but it's not straight. What about number 4? Is this one linear? Tricky, isn't it? This one is. Now, it doesn't look like y equals mx plus b yet, but could we write it easily as y equals mx plus b? Like, could I combine these two guys together? Sure. And I would get y equals 3x plus 2. So that one is linear. And one last one. What about this guy? Is he linear? Well, there's no squared and there's no square root. So I think it might be. But let's remember back to chapter 1.5 when you learned to solve for y. Let's try solving for y and see what happens. So to solve for y, I'm going to get 2y equals negative 2x plus 8. And then dividing by 2, I get y equals negative 1x plus 4. Oh yeah, I can write that as y equals mx plus b. And therefore the answer is yes, that one is linear. Okay, so recognizing linear is pretty easy. Look for equations that look very simple, no squares, no square roots, just a y and an x that you could write as y equals mx plus b. Okay, there's one last little concept, and that has to do with this. It's a vocabulary word. So perhaps you want to write down these two vocabulary words. The words are discrete and continuous. So there are two kinds of graphs that we're going to do in Algebra 1 and that you can do anywhere in life. Discrete and continuous. Let me give you the definition. In a discrete graph, the points are not connected. In a continuous graph, the points are connected. So it's going to ask you your assignment today, is this a continuous graph or a discrete graph? Or would this make a continuous graph or a discrete graph? Let's take a look at the difference. It's logical. First of all, let's go with this one. Fees for overdue books. Okay? So it tells you here that if you are 3 days overdue, you're going to have to pay a fine of about $2.25. So here is the question. Why did they not connect these points? There's a reason for it. And here's the reason. Can you at the library be 3.5 days overdue or 3.6 days overdue? No, they don't do that. You're either 3 days overdue or you're 4 days overdue, but there's nothing in the middle. And because there are no points in the middle, you are not going to connect, because when you connect, what you're really drawing is all the points in the middle. But there are no points in the middle for this one, so we would not connect those points. And this is what's called a discrete graph. Uh-oh, is discrete spelled with an I or an E? Hang on one second. I will confess I'm not the best at spelling. Let me make sure it's with an I. My apologies. D-I. All right, this is called a discrete graph. See, that's what you do. When you don't know how to do something, look it up. Like I didn't know how to spell discrete right now, so I looked it up. Let's take a look at Josh's car trip. That's me. He started at 160 miles from home, and then he drove at a regular rate. And after 4 hours, he was home. So here's the question. Can you drive for an hour and a half? Sure you can. Can you drive for an hour and a quarter? Of course you can. And if you drive for an hour and a half, could you drive 100.3 miles? Sure you could. So the point is that in this graph, there are an infinite number of points and they're all connected. And because of that, we're going to end up getting a line that's all connected, and that's called a continuous graph. See, it's logical. It's not like we just randomly connect if we want to. We think of the situation and we connect if it makes sense. Let's take a look at this one down here. This one's discrete, obviously, because these are not connected. And let's see why they didn't connect them. This is number of tickets purchased. Can you go up to the window and say, "Hi, good morning. I would like 2.5 tickets." No. And because we can't say we want 2.5 tickets, there's no point right there. And because there is no point right there, we're not going to take a line and connect these guys together because that would represent that there are points everywhere. And because there's no point there, it's discrete. All right, one last one. This here is time, and this here is snow. Can you have 2.5 hours? Sure. Can you have 1.25 inches? Sure. That means that there are an infinite number of points in here, and so they are all connected, and this is continuous. So the question is, can you have 1.5 of them? If you can't have 1.5 of them, it's discrete. You don't connect. If you can have 1.5, you can connect. Okay? All right. That's it for this one. If you take notes, maybe you should write down those two definitions. And back on slide number 1, perhaps you want to write down these keys. However, the rest of it you really don't need to write down. This one's pretty easy, isn't it? Okay, I'll see you guys next week. Bye-bye.